Hi, everybody. I'm Jacopo. It's the first time presenting at this workshop. It's been very exciting. I'm a PhD student here. I'm in computer science. My advisor is Jeremiah Sulam. And it's been great to hear about all the great things that everybody's been doing with diffusion models and reconstruction. And I was even happier to see on your slides, Webb, that the example question in the Zoom chat was, oh, Webb, but how can I trust this model? Because that's something that I care about, and today I would like to share with you all some of the reasons why I care and trying to convince you that there are things that we can do. Okay, so let me just figure this out. Nope. Oh, yes, thank you. Well, I think this slide is useless with this crowd, but yes, there are a lot of inverse problems that a lot of people care about. And yeah, this is something that we all do every day, and they are important for patient care and all the things that we do with imaging. In general, when we talk about solving inverse problems, there is like an axis of like which model I'm going to use, what assumptions I'm putting on the problem, and tractability and complexity of these models. In this talk, we're going to have the running example of like diffusion models and how we can put like uncertainty guarantees on these very black box models. But our contributions apply broadly to any point predictor with a heuristic notion of uncertainty. So we can use, for example, MC dropout. If we have like a ResNet with dropout, we can use it at inference time and have a variation. Or point predictors that have, for example, quantile regression that predict lower bounds and upper bounds instead of the mean for each pixel, for example. And just to get a sense of where we are on the spectrum. So right now, we're going to say, okay, I'm going to put it through my black box diffusion model, and I'm going to receive a bunch of samples. And all these images are equally likely. So if I were to take these reconstructed images, put them forward, I will get the same observation. So the question is, well, how much uncertainty is there in these samples? Because if we blow up details, we're going to see variations. So for example, here there's this that disappears across samples, some details down here change. And so what we're trying to do is drop any hope to model the posterior and just say, what can I do in a distribution-free manner when I assume that I have only access to finite samples from these models. So just to set up some notation, we're going to think of images or ground truth signals in d dimensions. We're going to have a forward model that is noisy with noise level epsilon, and we have access to a stochastic sampler f that solves this inverse problem. So d subscript y is the distribution that this model is spitting samples out from. And the best that I can hope for is that this distribution somehow was trained to approximate the true posterior, but we're not going to believe that. And with that, we're going to try and answer 3 questions. First of all, what happens if I fix the same observation in a sample multiple times, right? So the example is the variation. These are all from the same measurement. So how can I have guarantees on the samples from the same observation? And this is sort of like a variance question. Then, okay, perfect. We have a variance, but with variance, there's always bias. So where is the true signal that I'm trying to reconstruct? So how far is x hat from the unknown x that I'm trying to reconstruct? And then finally, can we leverage some semantic information about these images to get better uncertainty estimates? Okay, so first question. The general idea that we're going to be talking about today is that of confidence intervals. So the first thing that we're going to do is take our point predictor that predicts like the map at each pixel, the posterior mean at each pixel, and turn it into a set. So we take F and we construct C. Importantly, we don't need to change F. So all of this can be done post-training, just post-processing a fixed predictor that is given to me. And we're going to use ideas of conformal prediction, which is a distribution-free finite sample way of obtaining these confidence intervals that provide guarantee. And besides the math, the idea is, okay, if I have a distribution and I look at the distribution of every pixel from my diffusion model, what I can do is to take the lower calibrated and the upper calibrated quantile and construct these intervals. So now these lower and upper bounds will provide coverage in the sense of if I fix the same observation and I sample again, the same corresponding pixel of the new sample will fall within the sets with high probability. And this is the statement down at the bottom of the slide. So let's say I fix alpha and I say I want to provide coverage at 90%. So alpha is 10. I will sample 100 times from my diffusion model on the same observation. And for each pixel, compute these sets. I have 90% chance that the next sample will fall in that interval, entry-wise. So this is a guarantee entry-wise for every pixel in the image. Great. So these are some examples. Let's say this is the ground truth, this is the observation. I get the lower and the upper. Of course, the lower is darker than the upper. And the set size gives a sense of how much uncertainty there is. So the width of the interval says, oh, there's more uncertainty here compared to in other regions of the image. I don't know. But yes, these are tiny. Okay, great. Now, what is the thing that we're ultimately trying to reconstruct? The true signal X. So the next thing is, okay, now we have a notion of variance, that we have the conformalized blue intervals, but what happens if the point that I'm trying to reconstruct is outside of this interval, okay? And we can consider this as like a 0-1 loss, right? On average, we want to guarantee that no more than a certain amount of pixels are outside of the intervals. And this is what this 0-1 loss is computing, right? It's just the proportion of pixels that are not contained in their intervals. And then at the bottom is the kind of guarantee that we would like to provide. So earlier it was a high probability statement. Now we want an expectation, a risk that is controlled over the population, right? So in the future, I'm gonna get a new observation Y. I don't know the ground truth X, but I would like to guarantee that at least I know that on average is not more than epsilon pixels away from my reconstructed samples. Okay, how do we do this? Well, the idea is if I have a set, pixels are normalized 0, 1, so ideally I could always return 0, 1 for all pixels. That will control risk by definition because pixel will be in the interval 0, 1, but they're not very useful. So what we're gonna do is we're gonna stretch these intervals to the maximum level and then start shrinking. And we're gonna pick the smallest lambda such that this scaled version of the empirical risk over a calibration set that the model has not seen during training exceeds the tolerance epsilon. And again, this is just start large, shrink until this slightly different version of an empirical risk goes above epsilon. And that's the level that I should pick, okay? And again, the picture that I would like everybody to keep in mind is just, this just means add lambda, okay? Such that you include the pixels. Perfect. In high dimensional settings, such that the ones that we care about though, choosing the same scalar for all 200,000 pixels is very suboptimal in terms of the mean interval length, right? The uncertainty in the background is very different from the uncertainty in the ribs, in the heart, in the lungs, in the nodules. So the first idea is, okay, let's send this in high dimensions. Instead of choosing one scalar lambda, we're going to find a vector lambda that tweaks the little intervals independently. So each pixel can be tweaked by a different value, lambda j now. And the idea is going to be, well, usually the most informative intervals will have short interval lengths, will be short. So we frame this as an optimization problem, where we ask, we want to minimize the mean interval length, which is represented by the sum of the lambdas, if the sets are parametrized like in this additive way. And our constraint is that the risk should be controlled, which whatever lambda we land on, the risk should be controlled over the population. Okay, now the difficulty with this problem is that this constraint set is non-convex. And intuitively, our procedure will follow this two-step approach. Okay, first, up in the left, we have a two-dimensional pictorial illustration, where the red region is where I have bad predictors that do not control risk, and the green region is the one that I would like to optimize over, right? But its boundary is non-convex, so I don't trust optimizing this directly. What we're going to do is we're going to first find an anchor point that is a good approximation, and we're going to define how to find this approximation. And then what we're going to do, shrink. And shrinking in high dimensions just means going down the diagonal, right? If all the lambdas were the same, we would be optimizing along the diagonal. Any point along this line has the same lambda 1, lambda 2. So the original procedure was just start at the bottom, at the top right corner and shrink. What we're going to do is first we're going to shift the diagonal by solving an optimization problem and then backtrack. And ideally, this is what is going to happen. We're going to be able to find a solution that still controls risk, but has shorter mean interval length. And this is good because it's more informative. Okay. So to do this, of course, the D is very, very large. So we're going to reduce complexity of the optimization problem by dividing pixels in K regions, right? So we're going to find a K partition of the pixels that we like. This is, for example, with increasing number of regions, and the way that we're assigning pixels here is by quantiles of the residual. So let's say we pick quartiles, so K equals 4, we get the loss over a population, and then we assign pixels to how likely it is that that pixel has high loss or low loss. And we see that we do assign pixels based on sort of like spatial information. So the background is usually low error, so those pixels get grouped together, and then we can see sort of like the lungs, the border, the contour of the body, and features like that. Okay, so to run our procedure, first we're going to find the anchor point, and it's basically minimizing the mean interval length, where now we have K, so we need to keep in mind how large each of the K regions is, multiply by whatever lambda I'm going to pick for that region. And now the constraint, we're going to relax it. The 0,1 loss is non-convex, so we're just going to put hinges that are convex. And now we can solve this optimally because it has the constraint is convex. It has a global solution. So this is going to be our anchor point. And then we're going to backtrack along this shifted diagonal. And it's the same as what we saw earlier, where instead of smallest lambda, we have smallest lambda on shifted diagonal. Perfect. What does this give us? Here we have some example uncertainty maps. And importantly, one could say, oh, but I can do this by looking just at the standard deviation of the pixels. Right. But standard deviation does not provide distribution-free finite sample guarantees. These maps provide very precise statistical statements with them. First, we know that the next sample on the same observation will fall within the intervals, and also that the ground truth axis not too far, is no more than epsilon pixels away. Perfect. But we see something that we don't like about these maps, right? There's a lot of artifacts. For example, here, why do I have uncertainty outside of the body of the patient? Here we have these halos, as we call them, outside of what is actually in the image, because the lambda that we find come from the population, right? So what we would like to do now is to localize these maps on a particular patient. And how are we going to do it? Well, instead of assigning pixels by a notion of risk over the population, we're going to use a segmentation model and assign pixels to their organs, okay? So now we're going to parameterize sets by pushing the reconstruction through a segmentation model, and we're going to assign pixels according to whatever structure they belong to. Okay. So for example here, ground truth, measurement, and a segmentation on top of the reconstructed images. Importantly, the segmentation needs to be going through the reconstruction, right? Because we don't know what the ground truth is at inference time. Okay, and here, for example, we segment 9 different structures: kidneys, aorta, inferior vena cava, gallbladder, liver, stomach, all those. Perfect. Okay, how does the procedure change? Well, the main difference is that now the size of each group changes. because different patients will have organs of different sizes. So what we need to do is to find an anchor point by minimizing the expected mean interval length now. So we're going to do the same, and instead of using NK, we're going to put in the expected size of organ K, where we estimate this from data, okay? And then after we find this anchor point, again, what we're going to do is just find the smallest lambda along the shifted diagonal. Okay. And the nice thing about this procedure is it can be extended to per organ coverage. And we're going to see what that means in a second. But okay, same two-step procedure where now we're going to minimize an expectation of the size of each organ. What changes? Okay, these are sort of like the three different methods and the kind of maps that they produce. So first we have conformal risk control, tune one scalar lambda for all the pixels, and you see there's a lot of artifacts here. So the background even has uncertainty intervals. These are very weird uncertainty maps. Second best thing that you can do is do KCRC, so assign pixels based on a global notions over the population. Again, you find a lambda k, and you add it, and you still see that you have a little halos here and there that we don't really like. Or you could do the semantic version, and now we can rank organs in terms of how much uncertainty they contain. So for example, here we can see that aorta has more uncertainty than pancreas, then liver, spleen, inferior vena cava, stomach, left kidney, body, right kidney, background, and gallbladder. And now we have localized uncertainty maps for each patient. And these are the segmentation maps where each organ is colored accordingly to how much uncertainty there is. And then finally, the conformalized uncertainty maps, where we can see, for example, that now organs here get very different uncertainty compared to the previous two methods. And we can shrink those interval sizes. So again, here we see differences here, compared to the previous methods. And again, these maps carry very precise statistical meaning with them. And of course, this is useless if it doesn't provide actually shorter interval lengths, but it does. So that's also pretty nice that we can leverage this semantic information and get actually better uncertainty intervals. So you can leverage information to do something smarter. And then finally, this is what I meant earlier by controlling risk per organ, because basically what happens is methods can overcover, meaning the risk in the background is very, very below the tolerance epsilon, but most of the organs actually exceed the tolerance that I would like to set. And it's very difficult to tune this parameter per organ, unless you know where the organ is. So you do need a segmentation model. But once you do, you can tweak the procedure and guarantee the same level of risk across all organs at the same time, which is something that we couldn't do before. So the red bars are all below and all hit the tolerance epsilon. And yeah, just to recap this little story, we developed rigorous methods for distribution-free uncertainty quantification, inverse problems in CT in this case, but these can be extended to any inverse problem with any stochastic sampler. And the three main takeaways that I would like everybody to have is you can use calibrated quantiles to guarantee coverage of new samples on the same observation. We can use ideas of high-dimensional risk control with convex optimization to guarantee mean interval lengths for the uncertainty sets. And finally, improving performance of these sets by leveraging semantic information. And this was joint work with Webb, Matt, and my advisor. If anybody would like to use these methods, they're all on GitHub, and just funding acknowledgements. Thank you so much.
Quick question. Very good work. So speaking of the uncertainty, since you know the confidence level in terms of reconstructions, so my question here is that can you using that as a prior knowledge to further going back and improve your reconstruction?
That's a great question. So I think before we couldn't really do it. So okay, with KCRC, you don't really know where the uncertainty is, right?
Sure.
So that's not super duper actionable finding. But now that we know where the uncertainty is in terms of organs, then yes, that is definitely more actionable. For example, one could refine just do like a few gradient updates depending on the uncertainty maps on particular regions, for example, and just like adaptively say, oh no, this sample is great in this region, but if, for example, the uncertainty in the liver goes above something that I would like, let me just keep the rest of the sample fixed and do a few gradient updates, likelihood updates, just for that organ, such that I reduce uncertainty.
Got it.
That's a schema that could be maybe reasonable to use. Yeah.
Okay. No, thanks. Good work.
Of course. Great question.
Very interesting work. I really like it. Two simple questions. One, that since you use cordial to define and prove the first theorem, does that mean your underlying assumptions that the data is like a high-dimensional Gaussian distribution?
There's which theorem?
The first one that
No, sorry. This one.
yeah.
There's no, this is distribution free.
Okay.
Yes. So the trick is basically putting no assumptions. The best you can do is take the lower and upper quantiles and then pick the next sample, basically, to make sure that you're accounting for how many samples you're using to construct these intervals. But this works for any distribution because it just works on exchangeability of the ranks if the data is IID.
So if the data is the distribution is too complicated, how can you calculate the quanta?
This is just the empirical quantile.
Okay.
Yeah. So you just take the empirical CDF and take the first point such that the ECDF is above the quantile that you want. Yeah.
Okay. My second question is that when you do the optimization to control the semantic risk, right? Mm-hmm. Sometimes it's more meaningful to do minimax instead of do minimization.
Okay.
It's easy to change this to a minimax instead of minimization.
Where would the max be in this?
So for example, I'm thinking about, for example, you don't want to say all the organ above some risk, right? Mm-hmm. And you just want to focus on some region.
Yes.
Some region that the worst case, basically you want to think about the worst case scenario.
Okay, you want the
what's
worst
the best
case
you
organ.
can get.
Yeah, no. Great point. Yeah. You can do it. Yeah. It's you can do it either. So, you can take the max over the k's. Yes, you can. K is very small, so you can. It's very easy to take the max over the k's and just take that down. Am I making sense?
Yes, I think so. I'm just thinking about how to implement, how complicated.
Well, the easiest thing would be do it for all k and then take the max, since k is small. In a more complicated setting, where k may be too large.
For example, if I consider nuclear medicine like PET or SPECT, right? The range is very dynamic, mm-hmm. and it's much more dynamic than CT. And for some optical imaging, I think the same scenario that the dynamic range of the signal in your image is very complicated. And in this case, you want probably control some region that think about the worst case for that region.
Yeah. I think for we can work we can sit down and see maybe there needs to be some smart way of choosing which region to optimize over. That depends on prior knowledge. Yeah.
Thank you.
Of course. Thank you so much.
So your conformable prediction work, very nice. So one possibility, have you ever considered instead of using mean of all those lambdas, you try to compute some geometrical mean? Geometrical mean would be somehow related to volume, not just the marginal loss. So you see what I mean?
So instead of taking the mean interval length, taking the geometric mean.
Maybe multiple factors related to lambda multiplied together.
Oh, I see.
So I try to see what will be the, say in 2D case, what will be the region within which you have a prediction fall in. So that will be more related to probability.
I see. So I think that depends also in the way that, that depends how you parameterize your uncertainty sets. Now, the nice thing about this is that it's additive. If you start to have multiplicative factors in here, then yes, I agree that this...
You could use log to make multiplication still additive, but the geometrical interpretation will be a little different.
Yes, correct, yes. That's a nice idea. I didn't think about that.
Anyway,
Thank you.
Let's thank Jacopo one more time.